Here we go with alkenes and alkynes. We're going to talk about the unsaturated hydrocarbons. So some nicknames for the unsaturated hydrocarbons like alkenes and alkynes are olefins or olefins. Well, that's actually the same way, but potato, potato. Usually that would be somebody in the petrochemical industry that would use that term. Now you're going to notice that aromatic compounds, even though they contain unsaturation, double bonds and such, they are looking like alkenes, but they are not going to be considered in this chapter. They're not really the same because they have different structures and different properties. So alkenes and alkynes are unsaturated hydrocarbons, meaning that they have some form of unsaturation. So when you come through, you can do CnH2n for an alkene, and for an alkyne would be, oh, see, that's what I get for trying to talk while I write. Okay. CnH2n minus 2 for an alkyne. But that's only if it has just one of those in each one. So you can actually see that on the next slide. Alkenes contain at least one double bond. Alkynes contain at least one triple bond. So I don't know if you remember this from Gen Chem, but just kind of go over this to make sure. Carbon-carbon single bonds are the longest, and double bonds are the middle, and carbon-carbon triple bonds are the shortest because they're like springs. So as they go out and come back, the more that we have, the tighter and stronger they're going to be held closer together. So these are the general formulas. It is very helpful to know. We want to calculate the degrees of unsaturation. So I'm going to always look for that N value, how many carbons there are, and figure out how many hydrogens I have or how many hydrogens I need to make what I want. But that general formula is going to give me an idea of how many degrees of unsaturation I have. And that's going to tell me how many, the number of rings, double bonds, and triple bonds. So bonding geometry becomes important now because we talked about cis-trans and geometry that is not free to rotate. When we have all single bonds here, we have all single bonds in a molecule like this, they are free to rotate and generally rotate themselves so that they have bond angles that are all approximately 109.5 degrees. This would be tetrahedral. Now in ethene, where we have this double bond, not only do we have larger bond angles, about 120 degrees, we have a trigonal planar geometry, but now we're going to have some restricted rotation. So we're going to have restricted rotation and we're going to have the ability to have different items attached in different orders that are going to be stuck in that order. Now with a triple bond, we also have restricted rotation, but since we can only have one other item attached on either side, there are not going to be any geometric isomers present. So this one is going to have geometric or cis-trans is what we've been calling them, isomers. Bond angles here for around the triple bond are going to be linear, and the bond angle is going to be 180 degrees. So when we have restricted rotation, we have this possibility of having a couple different ways of putting things together. So double bonds bring up that restricted rotation. Like we said, triple bonds do too, but we can't have more than one item on a triple bond, so this is not going to play out there. Rings and double bonds is where we're going to see this. So with all single bonds, if we see a compound like, I'll draw it here. Oh, that's highlighter, excuse me. All right, H, C, H. So if we had this compound and we're comparing it to this compound, even though they're written on different sides, these are free to rotate and will eventually be on the same side, or we can put this molecule in this rotation without pulling it apart. Once we bring in these double bonds, we're going to have to actually pull the molecule apart in order to see that other possibility. So let's take a look at that. So here's our double bond. Put it in black. I'm going to highlight it in black. You won't be able to see it. All right, so here's our double bond. These are all the same molecule here, just different representations. We have both of these methyl groups. Now notice when we're talking about these compounds, we're going to be talking about groups that are the same. So we're going to look at groups that are the same. So we have methyl group here and here. Now when we're counting the chain, we're going to say 1, 2, 3, 4. But we can look at the hydrogens. It depends on the definition of cis-trans isomers that you're reading and where you're reading it. But we have to look for the same group being on the same side. Now the hydrogens are on the same side, but so are the methyl groups. When we look at this, we have cis because they're on the same side of the double bond. But when we come over here, they're on opposite sides of the double bond. They're going to be called trans. In order to make this molecule into this molecule, I can't rotate it, and this is why. So if I go to rotate this, if you remember from Gen Chem and just a little bit in the beginning, we talked about how these pi bonds form. So this is a sigma bond here, and these pi bonds form when we have this side-to-side overlap, or we have a front and back overlap of these p orbitals. We can't, because it's in two places, we can't rotate it unless, they rotate together. So we can't do that because if we rotated it, it would break. So this would show it broken. So this is a pi bond. Remember that if we have a double bond, we have 1 sigma and 1 pi. And if you have a triple bond, you have 1 sigma and 2 pi bonds. And a single bond is always just a sigma bond. So this bond would have to break the pi bond in order to rotate. So this is why we can't just rotate these molecules around. That's where the restricted rotation comes in. So if either carbon-carbon atom has 2 identical atoms, so we're looking for identical atoms like those 2 methyl groups or even the 2 hydrogens if you want to look at it, they have to have at least 2 different groups in order to be able to have cis-trans isomerism. So you're going to find a group in common to both ends. Now this is where we take a little bit of a liberal approach with the cis-trans definition in order to be able to expand it to be able to use it in this way. We're going to look for the same group on either. So here we have the methyl groups. We're looking down this bond and they are on opposite sides. So this one would be trans. And if we look down this bond here, they're both on the top. So it would be cis. So we have cis and trans. So the common group at each end is the methyl group here and here. Since neither of these carbons has 2 identical groups. So if this were just a methyl group and this wasn't there, we wouldn't be able to have cis-trans isomerism because these could be interchangeable and they would be the same, so that wouldn't be possible. But since that's not the case here, and we do have 2 different groups that are 2 of the same group on the opposite sides of the double bond, we can assign cis-trans isomerism. So to name this compound, which I'll teach you the rules in a minute, we're going to find the longest chain, 1, 2, 3, 4, 5. That includes the double bond. Double bond gets the lowest number. So this is going to be 2-pentene. Let me actually, because when I go to put this in the slide, that'll be in there. So 2-pentene. And then we have 2 methyl groups that we have to take into account. So we have well, sorry, no, we have one methyl group as a substituent. This is a substituent. This is part of the chain. So I have a methyl group at 3. I have 3 methyl. And then I need to say that they're on the same side. So I say cis 3-methyl 2-pentene. Sorry, there you go. Let's take a look at another one. The common group is the chlorine group here. So we have a chlorine on either side. This is our common group. Again, we expanded that definition a little. We need to follow through and find the longest chain to name it. So the longest chain is going to be butene. 1, 2, 3, 4. Both chlorines are on other carbons. There's not 2 of the same group here or here. So this will have cis-trans isomerism. So butene, where is the number? It's going to be 1. Butene. I'm going to move this again. I don't have to write that in there. I'm going to do it with the PowerPoint. Sorry. Getting ahead of myself. 1 butene. 1, where did that go? 1,2-dichloro. There's the one. Okay, I don't know what happened, but they're on opposite sides, so it's trans. It's at, the chloros are at 1 and 2, so 1,2-dichloro, 1 butene. I do have to have the 1 because it could be at carbon number 2, and it still would be butene. So trans 1,2-dichloro, 1 butene would be the name of this one. Now we haven't gone through the rules. Remember that I'm just going to go through the naming with you before we get to the rules yet, just so you can have practice later. I want you guys to pause this, please, and practice. Label each of the following as cis, trans, or neither. So please pause it and then label. First thing we're going to do is look for the same group, a common group on either side of the double bond, and then double check that these aren't the same and these aren't the same. So this does have cis-trans isomerism, and it's going to be opposite sides of the double bond, so it's trans. Now here, I don't have a common group. There are no common groups, and I have this group here. It is common, but it's on the same carbon, so there can't be cis-trans isomerism there, so it'd be neither. And here I have an ethyl group here and an ethyl group here. They're on the same side, so it'd be cis. All right, so that's what it means to have cis-trans isomerism. We're going to get into the IUPAC rules of naming, so let's do that. The parent name is still based on the longest chain. The longest chain now has to include the double bond. It has to contain the double bond. You're going to number the chain from the end that gives the double bond the lowest number. And we're going to change the ending to "ene." If I have more than one double bond, you just put a prefix in there, diene, triene, tetraene, for example. You can have, more if you have more, but we're going to probably keep it a little bit down. Name the branches and substituents just like we did with alkanes. If we have, give them the lowest number, then go in alphabetical order. We're going to use the same system that we learned with alkanes. Moving on to the next slide, we can take a look. Now, let's find the longest chain. Let's see here. Oh, I did the same thing again. 1, 2, 3, 4, 5. Or 1, 2, 3, 4, 5, 6. So 6 carbons is the longest chain. However, this one does not go through the double bond. So this one is not correct, where this one is correct because we number through the double bond. Now, the numbering system, the way I numbered it would be done this way, 1, 2, 3, 4, 5, to get the proper direction. So let's name these real quick. This would be a pentene, so this would be 1 pentene. And there is an ethyl substituent at 2, so 2 ethyl. Is there cis-trans isomerism? No, because this carbon of the double bond has 2 hydrogens, so there is no cis-trans. So 2 ethyl, 1 pentene for that one. Let's name these molecules. Why don't you practice it and give it a try? Go ahead if you want to. Otherwise, we'll just do them and then you can figure it out. First is find the longest chain. Now, these are sets. This is the condensed formula. This is the line formula, but both of these molecules are the same in each group. How many carbons? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So I'm going to have hexene. Because it's over propene, I have to number because the double bond could be here or here and still give me the same hexene. I just have to say where that double bond is. So the double bond is going to be at 1. So we would have 1 hexene, but you can alternatively say hex 1 ene. I would say most people say 1 hexene unless we have to do it this way to avoid confusion. Next up, we have our 1, 2, 3, 4, 5, 6 carbons again, but now we have a branch. So do we start numbering from the left or the right? We're going to start numbering from the right to give the double bond the lowest number. Substituent does not take precedence. The double bond does. 1, 2, 3, 4, 5, 6. So it's a hexene. It's still a 1 hexene, but there's a methyl group at 4. So it'd be 4 methyl. And again, because there's 2 hydrogens here, there are no cis-trans isomers for either of these so far. Here in this last one, what is our longest chain? 1, 2, 3. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Either way I do it, I could go this way, 1, 2, 3, 4, 5. Or I could say 1, 2, 3, 4, 5. But I cannot use this as part of the main chain. It's going to have to be a substituent because I have to include the double bond when I do this. So when I go to name it, I'm going to say 1, 2, 3. Well, I don't know. I have this in the computer. I don't know why. Doing it the old-fashioned way. 1, 2, 3, 4, 5. So I have 2 substituents, and those substituents are here, and they're both ethyl groups. So they are going to be diethyl, and they're going to come at numbers 2 and 3. So 2, 3, diethyl. 1, pentene. Again, no cis-trans. You can't have cis-trans on a terminal alkene because it's going to have 2 hydrogens. So we're just going to do a bunch of practice for now. And so pause it, try it, and then we'll look at the right answer together. So what is the longest chain here? The longest chain is going to be heptene. So 1, 2, 3, 4, 5, 6, 7, like this. Works, up or down works, they're both the same. That is our parent chain. Do I number from the left or do I number from the right? I'm going to number from the place to give the double bond the lowest number. 1, 2, 3, 4, 5, 6, 7. So this is different than we saw in the last chapter because if I were to number this way, my substituent would be 2, but I'm now numbering to give my functional group, which, not really quite a functional group yet, but my special character here, the alkene that we're learning about, that takes precedence and gets the ending of ene. So that's where I'm going to lower to give that one the lower number. So I have 2 substituents. I have an ethyl. That doesn't help when they're the same color. I have an ethyl and I have a methyl. So I have heptene, and the double bond starts at 3, so I'm going to have 3 heptene. I have a methyl group and an ethyl group. Ethyl comes before methyl, and then I'm going to number it. I'm going to have 6 ethyl, sorry, 3-ethyl, 6-methyl, 3-heptene. All right, naming alkynes, very similar to naming alkenes, except the ending is going to be -ine instead of -ene. So we change it to YNE. That means there's a triple bond there. Now, many times when you draw these out, because they're linear, you're going to see this. Now, this counts as 1, 2 in the carbon. And here too, there's a carbon here and a carbon here. So make sure when you get some practice counting these line structures, okay? We want to make sure that you're not getting something wrong just because we didn't talk about that they're written that way. Why are they written that way? Not that you won't ever see them, 1, 2, 3, 4, 1, 2, 3, 4, written like this, but this one is not technically correct according to that fact that it's linear. So sometimes if we're in a hurry, we'll write it like that anyway, but because it's linear, it should be written like you see here. So when we go to number this one, we're going to find the longest chain, and the longest chain is going to be 1, 2, 3, 4. Now again, both of these are the same compound here and here. They're just written in different type. Now I have a methyl group at carbon number 3, and this is going to be butyne. So I have 3-methyl butyne, 1-butyne, because it could be 2-butyne, right? So 3-methyl, 1-butyne. Now here, do I number from this direction or this direction? We have to decide. If I were to say 1, 2, 3, 4, my triple bond would have a 4. If I say 1, 2, 3, my triple bond starts with a 3. So I'm going to number from this way to that way so that I give my triple bond the lowest number. 1, 2, 3, 4, 5, 6, 7. I have a heptyne. I have a methyl group here and a methyl group here as substituents. So 6,6-dimethyl heptyne. And the heptyne starts at 3, so I would put the 3-heptyne. And just like we saw with enes, you could put hept3-ine if required. Because sometimes we'll have more than one type of functional group in a molecule, and we need to be specific about where that number is coming from. So you try. Number and name, pause it, and try. See what you get. Do we number 1, 2, 3, 4, 5, 6, or do we number 1, 2, 3, 4, 5, 6? Either way, my double bond starts with a 3, so I'm going to give bromo the smallest number and number from this direction. So what I get then is 1, 2, 3, 4, 5, 6. I have 2 bromo and 3 hexyne. This is a triple bond. So I'm going to have hexyne with a 3, so 3 hexyne, and bromo with a 2. 2 bromo, 3 hexyne. No cis trans, right? Can't have cis trans with a triple bond. Now, if there's cyclo, we're going to follow the same rules that we followed for cycloalkanes. So if we have a cyclo group, we're going to use the prefix cyclo, just like we did before. We're going to number the ring starting at one end of the double bond and numbering through the double bond. So 1, 2, or 1, 2. We have to go through the double bond with those numbers. Then you're going to give the substituent the lowest number possible. So in this case, we're going to number 1, 2, 3, because our substituent would have a 3 then, rather than a 1, 2, 3, 4, 5. So we want this to have the lowest possible number. 1, 2, 3, 4, 5 means it's a pentane that became a pentene because of the double bond. And the pentene is going to be at number 1. We're always going to have that be at the number 1 position unless there's more than one double bond. Then substituents, so we have a 3-methyl cyclopentene. Notice there's no number here. I don't have to put the number 1 if there is only one double bond, because it's always 1. Next one, we're going to number starting here, 1, 2, 3, rather than this way, 1, 2, 3, because that would give our substituent the lowest number. So 1, 2, 3, 4, 5, 6. A 6-membered ring is a cyclohexane. I have a methyl group and an ethyl group, and I have a double bond. Again, the double bond is always going to be at number 1, but I do have to number the methyl group. So this would be 4-ethyl, 1-methyl cyclohexene. All right. Pause it, practice it, see what you get. Should I say 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6? So if I go this way, I have substituents at 3 and 5. If I go this way, I have substituents at 4 and 6. So I'm going to pick 3 and 5. 3 and 5 are going to give me the lowest numbers possible. So I'm going to say 1, 2, sorry, I just did it the opposite way of what I said I was going to do. Good times. Okay. 1, 2, 3, 4, 5, 6. I have a chloro and I have a methyl. So this one's going to come first because it's C and then the methyl group. So I'm going to have 5-chloro, 3-methyl cyclohexene. So cyclohexene, we don't need a number 1 because we know we started at number 1 unless it was a diene. And then we have our 3-methyl and our 5-chloro. Methyl comes closer to cyclohexene, then chloro. So chloro comes first alphabetically. 5-chloro, 3-methyl cyclohexene. No spaces. It's like speaking German. They just put everything together. All right. Alkenes that have more than one are done using prefixes. So whatever the name for the alkane, a diene. So a triene. So let's look at this one here. We have 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. No matter how I number it, it's going to be the same. It's going to be a pent, a diene, and I'm going to have those at what numbers? 1 and 4. No matter which way I do it, it's 1 and 4. So 1, 4 pentadiene. I think I have this in there if I just click. Yeah, okay. So 1, 4 pentadiene. All right. If we look here, I have 1, 2, 3, 4, or 1, 2, 3, 4. My double bonds, no matter what, are at 1 and 3. 1 and 3, or 1 and 3. But if I go this way, my substituent has a smaller number of 2 rather than 3. So I'm going to number from this direction to that way, so from left to right. One, 2, 3, 4. I have a methyl group. So I'm going to have 1, 4 diene. But what is it? Butadiene. So then I'm going to have 2 methyl, hash mark, 1, 4 butadiene. Oh, whoops. Don't. Okay, we'll do that one next. There's my handwriting, and you can see the computer version of it in a minute. Now with the ring, same thing, but now I do have to put numbers in there because I have more than one. 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. Either way, it's going to be 1 and 4, 1 and 4. So I'm going to have I have 1, 4 cyclo pent, because it's 5, a diene. Now this is known as an isoprene unit. We're going to talk about that in just a few slides. I'll give you some more information on that. Here we have some more practice. I want you to try these. If they're not in your notes, just write them on the side or write them on a piece of paper and give it a try. Which way would you number them is the first way to ask the question. So would you number them, this way or this way? Figure that out and try your best to give them, to get your answers in there. So pause it, give it a try, and we'll go through the answers together. So we start numbering the first one, 1, 2, 3, 4, 5, 6. It's going to be a cyclohexene, and it's going to have a methyl group here at number 1, so 1-methyl-cyclohexene. Here we have a diene as our number 2. We would say 1, 2, 3, 4, 5, 6, but you could just as easily say 1, 2, 3, 4, 5, 6. And if we do that, either way, it's going to have our double bond numbers at 1 and 4. So 1 and 4, cyclohexadiene. Then we also have this one over here, which is a cyclopentene. We're going to have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 are our two options for numbering. By doing it this way, the red numbering, you end up with a smaller value for the methyl group here at number 1, but a larger methyl group number here. So even though this way, I wanted to show you that, hold on, 1, 2, 3 would be 1, would be 2 and 3, and those are both lower numbers. We only look at the first number being lower, so number 1 is lower than number 2. So we're going to go with the pink numbering rather than the red numbering system. And then we have 2 methyl groups, and the methyl groups here are at number 1 and number 5. So it'll be 1,5-dimethyl. Then we are going to say, what? Cyclopentene. So we don't need a number here because there's only one double bond. But honestly, if you put it, I'm not going to mark you down for it. I think it's would be fine to be a little bit more specific, right? All right, here's another practice for you. I want you to practice naming these, so pause it and practice. Here we have 1, 2, 3, 4, 5, 6 carbons. So we have hexa, diene, and those are going to be at 2 and 4. So 2, 4, hexadiene. This is octa, 1, 2, 3, 4, 5, 6, 7, 8. There are 2 double bonds, so it's going to be octadiene. It's just where are they? Well, they're at 1, 2, 3, 4, and 5. So 2 and 5, 2, 5, octadiene. Here we have 1, 2, 3, 4, 5. So we're going to have 1, 4, pentadiene. Pentadiene. And those 2 enes are at 1 and 4. Next one we have the choice of doing 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. Either way, you get the same answer. Since it's a diene, we do have to number this. It's going to be cyclohexadiene. And those 2 enes come at 1 and 4, but we also have a methyl group that we have to put in there. So 3-methyl 3-methyl 1,4-cyclohexadiene. Rolls right off the tongue, doesn't it? All right, so right back here, I'm not going to go back because it'll take me too many clicks, but I mentioned something called an isoprene unit. So this is an isoprene unit here. So we look right here, this is isoprene. There's so many different things to say about them, but they're very abundant in nature, alkenes are. Ethylene is a fruit ripener, and it promotes plant growth, but sometimes during harvest season, not all of the fruit is ripe, so some companies will put on what's called an artificial fruit ripener, and the double bond that are in the alkenes helps in the ripening process of fruits, so it's going to ripen the fruits faster. So it's actually a laboratory-produced derivative, and the farmers can spray it on their crops, and within 3 days they'll start to see ripening. But it has a very specific structure. So this is our very specific structure that we see that has 2 or more units of hydrocarbons. Okay, we see those 2 units of hydrocarbons. Each unit has 5 carbon atoms, 1, 2, 3, 4, 5, that are arranged in this specific pattern. So isoprenoids and terpenes are 2 of the ones that we see. Now, specifically, terpenes refers to anything that's occurring in a naturally occurring compound. However, modern technology, or terminology, I should say, modern terminology has become just a little bit less precise. So the terms are used interchangeably a lot of times. But the word terpene actually comes from an older spelling of turpentine, which is a cleaner, if you don't know that. It's a mixture of isoprenoids that are originally a resin from a terpene plant. So pretty cool. But this would have the name 2-methyl 1. Here, let's just measure it out here. Let's just write out 1, 2, 3, 4. So we have 2-methyl 1, 3. And what would this be? It would be a butadiene. Diene, because it's 4 carbons. So even though there's 5 carbons total in this, we have that branching carbon that comes up as a methyl substituent. Now, this is one of the most familiar sources, one of the most common ways that we're going to see these come across in naturally occurring compounds. So isoprenoids contain 2 to many of thousands of these units that repeat over and over and over again, and they play widely varying roles. So these are some isoprenoids that might be something you've come into contact with, and they're mostly in physiological parts of plants and animals, and they also have a number of commercial uses. So in living organisms, they're going to function from pigments to fragrances. So these are some of the things you're going to see on this slide. And they're going to also be involved in sex hormones and essential oils, if a lot of you are into essential oils these days. But in commercial uses, I don't have a picture of commercial uses, but in a picture, without lacking a picture, commercial uses can be flavorings, solvents, raw materials for chemicals, and other things. But one of the most common naturally familiar sources is rubber. Rubber is a polyisoprene, so that might be something that you're familiar with. Alkyne uses and well, we're going to talk about alkene properties, which are very similar to alkanes, but alkynes also have many uses, but mostly they're going to be in fuel sources, like they're fuels for welding torches, organic solvents, and starting materials that are going to be used to make things. Maybe so let's see. An alkyne is used to start the material to make vinyl chloride. It's a precursor that's used in making polyvinyl chloride, which is PVC. Okay, so that might be something that you're familiar with. Now, physical properties of these compounds, very similar to alkanes because we don't have any functional groups yet. No, not technically, right? We can count our alkanes or our alkenes and alkynes. They do have different bonding properties. They're going to have different reactivities than our alkanes, but there's no other elements involved yet. So they're still nonpolar. They still only contain London dispersion forces, and they're still going to be only soluble in nonpolar solvents like toluene and diethyl ether. They are usually liquid at room temperature and have a density less than 1 gram per milliliter.